Have you ever opened up a radio or seen the inside of a circuit board and noticed small discs or blocks labeled with strange codes? Those are capacitors, and what's fascinating is how something invisible between two metal plates can drastically change their behavior. That something is a dielectric, a material that doesn't conduct electricity but has a profound effect on how a capacitor works. In its basic form, a parallel plate capacitor in air has its capacitance defined by the equation C equals epsilon naught into a divided by D, where epsilon naught is the permittivity of free space, A is the area of the plates, and D is the distance between them. But here's the twist. Insert a dielectric between the plates and suddenly, the capacitor can store more charge for the same voltage. The new capacitance becomes C equals K times epsilon naught into a divided by D, where K is the dielectric constant, a number greater than 1. This happens because the dielectric gets polarized. It aligns its molecules in such a way that it reduces the effective electric field between the plates. Less repulsion means more charge can accumulate. This clever trick is used everywhere, from your phone's motherboard to industrial machines, enabling compact, high-capacity components.
Let's dig deeper. What exactly is this dielectric constant K? By definition, it's the ratio of the capacitance with the dielectric to the capacitance without it. That is, K equals C divided by C naught. Since the dielectric always reduces the field, the result is always an increased capacitance, so K is always greater than 1. This number depends entirely on the material's molecular structure. For example, mica has a K value of around 2.1, while water has an astonishing K close to 80. Now let's connect this to the electric field. When a dielectric is inserted, the new electric field E becomes E equals E naught divided by K, meaning the stronger the dielectric, the weaker the net field. Visual cue here. Imagine two diagrams side by side. One capacitor without dielectric and one with it. The one with dielectric shows fewer field lines, representing reduced net field. This ability to tweak the field strength and capacitance is what makes dielectrics so valuable in electronics.
Now here's an exciting question. What happens to the energy stored in a capacitor when we insert a dielectric? The basic formula for energy stored is U equals 1/2 into C into V squared, where C is the capacitance and V is the voltage. Let's take two cases. Case 1, the battery stays connected while inserting the dielectric. Since voltage V remains constant and capacitance C increases, energy U also increases. Case 2, battery is disconnected before inserting the dielectric. Now, charge Q is constant. Since Q equals C into V, an increase in C leads to a drop in V, and the energy stored actually decreases. So, whether the energy goes up or down depends on the condition of the system, voltage fixed or charge fixed. This principle is used in devices like variable capacitors in old-school radio tuners, where rotating a dielectric changes the tuning frequency by modifying capacitance.
Let's take a microscopic peek now. What's happening inside the dielectric? When placed in an electric field, the molecules of the dielectric align in such a way that they create small dipoles, tiny positive and negative charges facing opposite directions. This alignment is called polarization. These induced dipoles generate their own internal electric field, and this internal field always opposes the external one. So, the net field inside the capacitor becomes E equals E naught minus EP, where EP is the polarization field. This reduction in net field is exactly why more charge can be stored, because the same voltage now causes less opposition inside. But beware, every dielectric can only withstand so much. If the electric field becomes too strong, the dielectric breaks down and starts conducting. This threshold is called dielectric strength, a critical parameter for real-world capacitor design.
So far, we assume the dielectric fills the whole space. But what if it only partially fills the gap between the plates? When a uniform dielectric completely fills the space, it's simple. C equals K times epsilon naught A divided by D, straightforward. But if the dielectric is only partially filling the space, we get some clever math. If the dielectric divides the distance between plates, like 1/2 dielectric, 1/2 vacuum, it behaves like two capacitors in series. If it divides the area, say half the plate area is covered with dielectric and half is not, it acts like capacitors in parallel. Let's solve a challenging example to see how this works in numbers. Problem: a capacitor with plate area 0.02 square meters and plate separation 2 millimeters is half filled with a dielectric slab of K equals 4. What's the net capacitance? Step 1. We divide the setup into two capacitors in series, one with dielectric, one without. Each has thickness d by 2. Step 2. Apply the formula for each part. C equals K epsilon naught A divided by D by 2. C equals epsilon naught A divided by D by 2. Step 3. Combine them using the series rule. 1 by C equals 1 by C plus 1 by C. Step 4. Substituting and simplifying gives us C equals to K epsilon naught A divided by D times K plus 1. Step 5. Plug in the values. Use epsilon naught equals 8.85 into 10 to the power minus 12 farads per meter and you'll find the result in nanofarads. It's a beautiful example of how physics blends geometry, material science, and electric field behavior into one neat calculation.
Let's quickly recap what we've uncovered in this fascinating journey through dielectrics. We learned that inserting a dielectric increases the capacitance of a capacitor by reducing the effective electric field. The key factor here is the dielectric constant, or K, which tells us how much the capacitance improves. We also explored how energy changes depending on whether the system holds voltage constant or charge constant, and how polarization reduces internal fields. Most importantly, we saw how real-world designs use uniform and partial dielectrics to optimize capacitor performance. From simple circuits to satellite systems, dielectric behavior in capacitors is at the heart of modern electronics. I hope now you understand how something seemingly as simple as a non-conducting slab can transform the performance of a capacitor. See you in the next topic, where we dive even deeper into the wonders of electric fields and potentials.